Okay, welcome again. I'm going to be talking today basically about my school project. I know it has a very fancy name, but it's essentially a school project. So, and before I actually tell you what it is, I thought I should first give you some background on how I got to this idea to implement this project. So, first thing is about actors. So, actors recently became very popular, right? They existed forever in Erlang, and at least from the Scala perspective, you know, Scala kind of popularized them. And then you have a bunch of frameworks. The most famous one, Akka, that extensively use actors. But what I was thinking essentially is you know, and what I noticed is, even though actors are pretty good for solving concurrency problems, right? I mean, they kind of encompass and guard the state and make sure that operations on that state are done one at a time because there's this mailbox and the messages get fed in and all that. But then I also noticed that, you know, once you start using actors and you want to kind of send a computation to some remote node, to some other box, people tend to use actors as well. They just say, okay, if I'm using this on my local machine, you know, if I want to execute something remotely, I just send that to a remote actor. And we've kind of seen this with a lot of other technologies as well, that once you kind of like something, you tend to use it for everything, even though it might not be the best fit, but you can typically solve it. But there are actually a couple of problems, and our very own Paul Chusano actually some time ago wrote a blog article on the topic of what is wrong with actors. The main underlying kind of theme was that they're not composable. That created a lot of buzz, that blog article. But the way I was thinking was, what if you just have something that is stateless in its nature? Let's say a pure function. So you have something that is computationally intensive, and you just want to send that pure function. You want to send the function and the parameter on which that function is going to be applied remotely, and then just get the result back. For that kind of stuff, you don't really need a remote actor. If you think of it, I mean, there's no state, and then it doesn't matter, you know, are those kind of event-based actors or they're not. You basically just want to have a server on the other side. I call it a remote function application server that would just accept that function and the parameter, do the computation, and send the result back. And obviously, this only makes sense if it's really computationally intensive. I'm talking about hard math, because the latency and the overhead of sending over the network is prohibitively expensive for a lot of things, right? So basically, that's one area where I think the actors are not good for, and that's the data parallel area. So if you imagine an array of some data, or let's say a matrix, and you just want to apply the same computation to all the elements of that data structure, an array or matrix, it's kind of like embarrassingly parallel. There's no communication in between, and you just want to have the computation applied as soon as possible. And in that case, actors kind of just represent the overhead. One proof of that, I think, is the Scala parallel collections library, which is a 2.9. So I'm not going to talk about that because Seth is going to cover that next month. But if you think of it, why? I mean, actually, let me ask you a question. Using what kind of framework was the Scala parallel collections library implemented in? Who can tell me?
What was that again?
The Scala parallel collections library. You guys know the concept, right? So you have, let's say you have a list, right? You have a huge list, and you want to perform a map operation, and you want to perform that map operation, or like a filter, let's say, on all the elements. That's an embarrassingly parallel problem, right? So you can do that in parallel. There are no dependencies between them. So they used a fork join framework to implement that. They didn't use actors, right? Because actors in that case would be really just an overhead. It was the fork join framework. I think Doug Lee is the author of that framework. Moving on. MapReduce. I also observed that when people think these days about doing some computation or doing any kind of processing in a cluster, this is the first thing that comes to their mind, MapReduce. Oh, that's a MapReduce problem. If you originally, I mean, again, it's like one of those examples where you can use MapReduce for a lot of stuff, but originally, MapReduce was really just meant for large data sets and basically processing a lot of data and kind of aggregating that data. And it was really meant for data-intensive applications, not for computationally intensive applications. Although I said you can solve, you can try to fit computational intensity into MapReduce, but it initially or originally it wasn't really meant for that. And when I say computational intensive, so I said it's hard math. So some examples are, let's say, like Monte Carlo simulations, or if you like rendering 3D scenes, or doing some operations like linear algebra operations on like large matrices. Those kinds of things. CS264 is the course that I took this spring at Harvard Extension School. The title of the course is Massively Parallel Computing. I took that in my spare time, the very little spare time that I have with a full-time job and a family with 2 kids. But I took it because it sounded so interesting, and parallel computing is one of my areas of interest. So I thought, there's so much to learn. It's been a while since I went to grad school, so I thought I can kind of pick up on some knowledge. Unfortunately, it was a lot more intensive than I thought it would be. The reason is it's offered in parallel with Harvard University and Harvard Extension School, so they didn't really take into account that there are people who work and study. But anyways, and also the unfortunate thing was there was a lot of emphasis on CUDA programming and GPU. I kind of learned that a lot. There was also some Hadoop and some other stuff, but a lot of it was kind of emphasis on GPU. But the reason I'm mentioning this project is this course is that for we got to kind of choose some final project to work on. That was almost half of the grade, and I really wanted to do something with Scala. We were constrained with technologies. It either had to be something with CUDA, or Hadoop, or using 0MQ. And I picked 0MQ. When we were learning about 0MQ, by the way, is there anybody who used or is using 0MQ? Okay, one person. So when I was listening to the talk about 0MQ, there was one lecture. It was as if I was listening Jonas Bonner's talk about ACK. It's essentially the same principle. It's along the lines that concurrency is a hard problem to solve. Only very few people get it right. Synchronization and locks are very bad, and all those reasons. And really, we should do it by doing message passing. So the same way you have in Akka, you have actors, and they pass messages between themselves. In the 0MQ world, you have threads which pass messages between themselves. But that's just like one of the things. So really, 0MQ is like is considered to be a socket library, but it really also acts as a concurrency framework. And they kind of made it language agnostic because the main stuff was done in C, but there are bindings for all kinds of languages. There's not one for Scala, but there's one for Java, which was good. The nice thing, there are a couple of nice things which kind of caught my attention and why I chose to use 0MQ as a technology for my final project. One of them is that it is message passing, but they implemented a lot of patterns. And one pattern which I liked is called divide and conquer. So basically, what you do is, if you imagine a world where there's a master node which has some work that has to be done, and there are all these worker nodes just ready and hungry for work to kind of process the stuff, basically. You basically just say on the master side, you bind to a socket. And this socket is not a typical network socket where you just say, okay, I'm going to connect to that other node and send those messages. When in 0MQ world, when you bind to a socket, there are multiple threads behind it because it can establish multiple connections. So in this divide and conquer pattern, it basically fans out. You can say if you want to use divide and conquer, it's going to fan out, basically load balance all the messages to all the worker nodes. And the worker nodes just basically say, I connect to this socket. And it's really nicely decoupled in a way that you don't need to do any synchronization. Say, I have to first bring the master, or first the worker, or vice versa. You can just bring the master, it will just bind to the socket and wait until there's somebody to consume that message. And then you can bring up the workers, or you can do vice versa. And also it makes the workers dynamic. So you can add or remove workers, they can die or whatever, without really affecting the master. Whoever is there is going to consume the message, and that's all the master cares about. The other good thing was 0MQ does the automatic buffering. So if the worker for some reason is slow to process and there are a lot of messages incoming, it implements buffering for you, and it's kind of going to queue them up. And if it sees that the buffer is really growing large, it's kind of going to tell the worker to kind of slow down. It's going to, I think at that point it's going to block if the worker is really having a hard time processing those messages. And the nicest thing, which I didn't get to use that much, is that when you implement your application using 0MQ, so you have all these threads and message passing, you don't have to change anything if you want your application to be just between multiple threads in the same process, or between multiple processes on the same machine, or between multiple machines in a cluster. The only thing you change is just the transport URL, to say TCP or something else. Everything else is really the same concept. You really have just different entities talking to each other, exchanging messages. And that was, I thought, very nice. And then lastly, as I mentioned, there's Scala parallel collections. And the nice thing about that we'll see in the next meeting is when you want to perform these operations on a collection in a parallel way, in the case of Scala parallel collections, that's using multiple threads in the same process, you basically just say .par on a collection, let's say a list or array, and you get this kind of parallelized list. And everything else is kind of just transparent to you. So you can use the same API you use for sequential collections, and it's just really nice that it's kind of, the whole API is you're kind of isolated from the fact, although you are aware that it's a parallel collection. So that's how I got the idea to do something I called RFAS, Remote Function Application Server, which basically is, shall I say, it consists of two parts. So one part where you use it as basically a framework, so you implement your application and you just import a library that enables you to kind of gridify your collection. So let's say you have for now there's only lists and only 3 methods implemented, map, filter, and flat map. So essentially what it does, it says, okay, if you have some computation, which is going to be intensive, and you can represent that as a collection, you just call that grid on that, and I'll show you that in the client code. And then all these operations on multiple elements are going to be performed remotely, using all the available nodes in your cluster. And then as a result, you're going to get back basically a new collection which contains those new elements.